Section 2.3 is where we're going to start to tie together some of the things we've been learning about in the earlier material. And you're going to find as we go through that the material tends to build on previous stuff, which is why it's so important that you master some of these skills. So in this section, we're dealing with the momentum principle, and this is called the update form. The reason it's called the update form is because it's telling you if you know your initial momentum and some time plus the force that's exerted on it, you can figure out what the momentum is at a later time. In other words, you can update the momentum. Now, this equation right here is actually the same as this equation that we'd seen in the previous section. They're both the momentum principle. They're just different forms. And one thing you need to be sure that you can do is that you can derive one from the other. You see the connection between the two. That's a really important thing that you be able to do. Now, there are instructions on page 54 on how to go about actually applying the momentum principle, and there are several steps. These are going to be part of the problem-solving strategy, and what you'll need to do is list some of these things. For instance, the first thing you need to do is choose your system and your surroundings. Now, in a lot of our problems, that's going to be pretty obvious, but when you get to some more complex systems, it's not going to be quite as easy. So it's important that you start practicing skills in very easy problems so that when you get to the more challenging situations, this stuff is kind of second nature. So we choose our system and our surroundings, by which we mean the system is the thing we're actually interested in. So if we have a car traveling down the road and there's wind blowing on the road and the road's all rough, the system would be the car itself, including the wheels and the engine and all that. So that would be our system. The surroundings then would be the road, the earth, the air, the things that are pushing on it. And so once we've chosen our system, we can then make what's called a free body diagram. The free body diagram is simply a diagram that shows the forces exerted on a particular object. Then we go ahead and choose our initial and final times. And notice these aren't necessarily the initial and final times for the whole problem. Sometimes when a problem needs to be broken up into smaller pieces, we'll have several initial and final times. And sometimes they'll change roles. So choosing initial and final times is an important skill to practice. Once you've chosen your initial and final times, you can then go ahead and apply the momentum principle equation, usually to find out what the final momentum is. And then you're not done once you've got an answer. You actually need to go ahead and check your units as well as the reasonableness of your answer. We're not really interested in the number that you get that comes out of these equations. That's not the important part. The important part here really is the process of solving these problems and checking them. So don't just focus on getting that number. That number isn't terribly meaningful because that only applies in one particular situation, but this whole strategy of solving these problems, all of these steps, this is a skill that you can apply in many different situations. Now, as you go through this chapter, they also talk a little bit about what happens when you start dealing with things like relativistic speeds. And really, the only thing you need to worry about right now is that your equation for momentum, you've got this gamma factor here. And for relativistic speeds, relativistic meaning relating to Einstein's theory of relativity, which typically deals with speeds that are close to the speed of light, close to c. At these relativistic speeds, gamma typically takes on some large value. Now, fortunately for us, at low speeds that relate to our everyday life, gamma is almost 1. It's so close to 1 that most measurement tools can't even detect any difference between the relativistic momentum equation and the Newtonian approximation. So when you're dealing at relativistic speeds, you'll have to include this factor of gamma, which you can calculate from this. One thing I do want to notice, sometimes this v is given as a fraction of c. For instance, we'll say that the velocity is 0.88 c. Now, the nice thing is when you go to plug it in this equation right here, v over c, we'll get 0.88 c all over c squared. These factors of c cancel, and so this term right in here is simply going to be the square of that number. It's just kind of a handy little trick. One last thing that's pretty important in this section is calculating average velocities when the velocity changes. In chapter 1, we were calculating average velocities from positions. But if we know the velocities at two different times, we can also calculate an average velocity. Now, this graph right here shows what the velocity versus time curve would look like when the force is constant. If the force is constant, that means that the rate at which the velocity changes is also constant. And so it's just going to be a straight line. Now, to find the average over this whole time, we can just calculate v initial plus v final over 2. And it turns out that that number is right here in the center. And the reason that this becomes important is if you try to figure out how far something has moved, you have to figure out, well, what velocity do I use to calculate the distance traveled? If I use v initial alone, well, that's going to give me a distance that's too small. If I just use v final, that's going to give me a distance that's too large. By using v average, I can then figure out how far something has traveled and get just the right answer. But again, this is only when we're dealing with a constant force. So here's an example of a non-constant force. This is a velocity versus time graph showing an object that's moving with a non-constant force. And so here is my initial velocity. My final velocity is up here. Now, if we go ahead and just calculate v initial plus v final over 2, we end up with this value right here, which clearly is not a very good representation. It's almost v final. But the average value is actually down in here. It's because this thing spends so much time at this very slow velocity. So for a non-constant force, this approximation is not so good. In certain circumstances, we may explicitly state that we're not going to use this approximation. So this equation right here is what we will use. It's only totally accurate when the forces are constant. When the forces are changing, this will come up when we talk about gravitational forces and electrostatic forces. When those forces are changing, then this equation doesn't give you a real good approximation, and we'll probably use something a little bit different.